Somewhere in your music collection, on a record you have played so many times the grooves have gone soft, or buried deep in a playlist you made at 2 a.m, there is a sound that you cannot quite name. It is warm and it hums. It has the weight of copper wire and the shimmer of something alive. It sounds, in the most specific and inexplicable way, analogue. Like electricity moving through real components, like physics. And yet the instrument that made that sound contains no coils, no capacitors, no hand-wound transformers. What it contains at its heart is a small rectangular piece of silicon designed by engineers in Dallas, Texas, for the entirely unromantic purpose of processing radar returns and compressing telephone calls. This is the story of how that chip, built for military precision and industrial efficiency, ended up becoming the secret engine of one of the most emotionally resonant art forms of the 20th century. Nobody planned it. Nobody at Texas Instruments ever looked at a circuit schematic and thought, this will make someone cry on a dance floor in 1997. But that is precisely what happened. And the fact that it happened by accident makes the story considerably more interesting than if it had happened on purpose. To understand what Texas Instruments gave to music, you first have to understand what Texas Instruments was. Not what it became, and not what it is today, but what it was in the early 1970s, when the world still thought of it primarily as the company that put a calculator in your shirt pocket. TI had been founded in 1951 as Geophysical Service Incorporated, an oil prospecting outfit that pivoted into electronics during the Cold War and never looked back. By the mid-70s, it was one of the most powerful semiconductor companies on Earth. Its engineers had invented the integrated circuit, or at least one of the two men who simultaneously and independently invented it, worked there, which is a detail that still generates passionate arguments at electronics history conferences. The point is, this was a company that understood silicon at a molecular level. It understood precision. It understood the cold, clean logic of mathematics, performed at speed. What TI was not, in any meaningful sense, was a music company. Its customers were the Department of Defense and the Bell system. Its product catalog read like a procurement officer's dream. Analog to digital converters, memory chips, telecommunications ICs, components for radar, sonar, and secure communications. The engineers who walked its corridors in Houston and Dallas thought in terms of bandwidth and signal-to-noise ratio. They thought in terms of throughput. The word warmth, as applied to a piece of electronic equipment, would have earned you a puzzled look in any of TI's engineering divisions during the Carter administration. Warmth was not a specification. Warmth was not something you could write on a data sheet. The first hint that something extraordinary was coming arrived not in a military application, but in a toy. In the summer of 1978, Texas Instruments unveiled the Speak and Spell at the Consumer Electronics Show in Chicago. It was a brightly colored plastic device about the size of a hardback book, aimed at children learning to read, and it could speak. Not play back a recording, actually synthesize a human voice from mathematical data stored on a chip. The team that built it, led by an engineer named Paul Breedlove, had done something that had never been done before. They had crammed an entire model of the human vocal tract onto a single integrated circuit. A chip the size of a fingernail was performing. In real time, the mathematics required to simulate the physics of lips and tongue and throat. The chip was called the TMS 5100. Texas Instruments described it, quietly and with characteristic understatement, as the first single-chip digital signal processing device in the industry. What made the TMS 5100 remarkable was not simply that it could talk. What made it remarkable was the method it used to talk. Rather than storing recordings of words, which would have required far more memory than was available or affordable, the chip used a technique called linear predictive coding, or LPC. LPC works by modeling the physical behavior of the vocal tract, the shape of the mouth, the resonance of the throat, the way air moves through the larynx. It reduces the human voice to a small set of mathematical coefficients, a handful of numbers that describe the physics of speech at any given moment. Feed those numbers back through the right equations, run the calculation fast enough, and out comes a voice. The speak and spell was not playing a sound. It was computing one. Every syllable it produced was the real-time output of a mathematical model running on a chip no larger than your thumbnail. That distinction between playing back audio and mathematically generating it would turn out to be the key that unlocked everything that came after. The TMS 5100 was a proof of concept. It demonstrated that a single chip could perform real-time mathematical modeling of a physical system, in that case, the human voice, with good enough fidelity to be useful. But it was a narrow tool, designed for one job. What TI's engineers began working on in 1980 was something far more general, something that could model not just a vocal tract, but any system that could be described mathematically. The project was led by two engineers, Ed Codell, who designed the initial architecture, and Surinder Magar, who joined TI that same year to optimize the design around the specific demands of digital signal processing. They were not thinking about music. They were thinking about radar returns, about telephone compression algorithms, about the kind of dense, repetitive mathematical work that was overwhelming conventional microprocessors. They were thinking, in particular, about one operation that DSP required above all others: multiplication. Multiplication is, on paper, a simple operation. But at the speeds required for real-time signal processing, it becomes the bottleneck through which all other computation must pass. Every digital filter, every FFT, every compression algorithm reduces eventually to a repeated sequence of multiply and accumulate operations. Multiply a signal sample by a coefficient, add the result to a running total, repeat. A general-purpose microprocessor in 1980 could do this, but slowly and clumsily, requiring multiple clock cycles per operation. What Codell and Magar built was a chip where a single multiply and accumulate could complete in 200 nanoseconds, 200 billionths of a second. The chip they unveiled at the IEEE International Solid-State Circuits Conference in February 1982 could execute 5 million such operations per second. For comparison, the Intel 8088, powering the first IBM PC, released just 7 months earlier, could manage perhaps 200,000 or 300,000. The TMS 32010 was, in the specific mathematical territory that mattered for signal processing, in a different universe entirely. The chip was formally released as a product in April 1983, announced at a conference on acoustics, speech, and signal processing in Paris. It cost $500 per unit at launch, which made it expensive even by professional standards, and it sold roughly 1,000 units in its first year. The customers who bought it were primarily telecommunications engineers and defense contractors, exactly the audience TI had designed it for. The chip went into modems, into medical imaging equipment, into military communication systems. It went into sonar arrays and radar signal processors and telephone switching equipment. It did not go into synthesizers. Nobody was thinking about synthesizers. The chip was doing serious, purposeful work. It was calculating the paths of missiles and the compression ratios of telephone networks. And somewhere on the other side of the world, in small studios and university music departments, a different kind of engineer was beginning to ask a question that TI had never thought to answer. The question was deceptively simple. What is an analog synthesizer really? Strip away the wooden panels and the patch cables and the voltage-controlled oscillators and the hand-wired filters, and what are you left with? You are left with physics. Specifically, you are left with the physics of electricity moving through passive components. A resistor resists. A capacitor stores charge and releases it. An inductor resists changes in current. An analog filter is just a resistor and a capacitor arranged in a specific way, and the sound it produces, that gentle roll-off of high frequencies, that warmth, that sense of something organic at the edge of the waveform, is the sound of electricity behaving according to the laws of physics. By the early 1980s, a small number of researchers in the field of computer music had begun to notice something. The mathematics that described those physical behaviors, the differential equations that governed how a capacitor charged and discharged, how a filter responded to a sweep of frequency, those equations looked very familiar. They looked, in fact, almost identical to the equations that digital signal processors were built to solve. This was the insight that changed everything. An analog filter is a physical implementation of a mathematical function. A digital signal processor is a device that evaluates mathematical functions at speed. Therefore, and this was the leap, the moment of serendipitous connection, a DSP could, in principle, emulate an analog filter. Not by copying it, not by recording its output, by computing it, by running the same equations that the physical components were solving in hardware, but solving them instead in software, thousands of times per second, on a chip made of silicon and logic gates. The resistors and capacitors would be replaced by numbers. The warm, physical behavior of analog electronics would be replaced by arithmetic. And if the arithmetic was fast enough, if the chip could crunch those numbers faster than the ear could perceive any gap between calculation and sound, then the result would be indistinguishable from the real thing. This was not yet called virtual analog synthesis. It did not yet have a name. It was just a mathematical observation, written in a notebook by someone who understood both circuits and equations. But it was the seed of everything. The practical barrier was time, or more precisely, the lack of it. To model an analog synthesizer in real time, to play a note and hear it immediately, with no audible delay between the key press and the sound, required a chip that could run the necessary equations fast enough that the latency was imperceptible to a human musician. The human ear, in live performance, can detect delays as small as a few milliseconds before they begin to feel wrong. A DSP running a complex filter model needed to complete the full mathematical cycle somewhere in the range of 20 to 40 microseconds per audio sample. That meant millions of multiply and accumulate operations per second. It meant, in short, a chip like the TMS 32010. The chip TI built for radar and telephony turned out to have exactly the computational profile required for real-time synthesis. The speed that made it ideal for processing missile tracking data was the same speed that made it capable of computing in one uninterrupted mathematical flow, the equivalent of a hand-wound copper coil. Through the mid-1980s, this idea moved slowly through the research community. It appeared in academic papers on computer music and digital audio. It was discussed at conferences where computer scientists and musicians occupied the same rooms and talked past each other with great enthusiasm. The Stanford Center for Computer Research in Music and Acoustics, known as CCRMA, and IRCAM in Paris were both working on related problems. How to model physical systems digitally. How to simulate the behavior of acoustic instruments and software. The phrase that began to circulate in these circles was physical modeling. The idea that you could replace a physical object with a mathematical description of how it behaved. A violin string, a tube of air, a filter circuit. All of these were, from the DSP's point of view, the same problem. A set of equations that needed to be solved quickly and repeatedly. Texas Instruments, making modems in Dallas, had accidentally handed the music world the tool it needed to make this possible. The company that first turned this academic insight into a commercial product was not one of the established giants of the synthesizer industry. It was not Roland, working from a gray office park in Hamamatsu. It was not sequential circuits, or Oberheim, or any of the American analog houses whose instruments had defined the sound of popular music in the 1970s. It was a small Swedish company called Clavia, founded in 1983 by a pair of engineers named Hans Nordelius and Mikael Karlsson, operating out of Stockholm. Clavia had been making electronic drum pads and MIDI controllers, useful, modest products, competently executed, not particularly notable. But in the early 1990s, Nordelius began asking a question that would come to define the decade. If DSPs could model the behavior of physical systems, could they model the behavior of an analog synthesizer? Not a violin, not a trumpet, an oscillator, a filter, an envelope generator. Could you take the circuit of a Minimoog, one of the most beloved and analyzed synthesizer circuits ever built, and describe it in mathematics, and then run those mathematics on a DSP in real time, and have the result sound like the original? The answer, Nordelius discovered, was yes. And the result did not merely approximate analog sound. It was, in the ears of the musicians who first played it, indistinguishable from the real thing. Or rather, it was something slightly different, something slightly better. It had the warmth of analog circuitry without the instability. It had the responsiveness of a physical instrument without the tuning drift. It stayed in tune in cold venues. Its oscillators did not waver. And yet it breathed. It moved in the way that analog instruments moved because it was computing the mathematics of that movement, sample by sample, in real time. The instrument Clavia built around this engine launched in 1995. It was red, vividly, unmistakably red, in an industry that favored gray and black, and it was covered in knobs in a way that no digital synthesizer had been since the early 1980s. They called it the Nord Lead, and they gave it a subtitle that was also a manifesto: No Samples. The phrase virtual analog synthesis was coined by Clavia at the Nord Lead's launch. It was new terminology for a new category of instrument, and it spread rapidly. The Nord Lead sound engine was generating its waveforms entirely in real time, computing sawtooth waves and square waves from scratch on every audio sample rather than reading them from a stored ROM, as nearly every other digital synthesizer of the period was doing. The difference this made to the sound was profound and immediately audible to anyone who compared them side by side. There was a liveness to the waveforms, a subtle unpredictability, a sense that the sound was being created in the moment rather than retrieved from a library. Critics and musicians reaching for descriptions consistently returned to the same word. They called it warm. The cold digital mathematics of a chip designed for telephone compression was producing warmth. Texas Instruments, reliably, had no comment. Clavia was not the only company following this path. In Germany, Waldorf Music, inheritors of the wavetable synthesis tradition, developed by Wolfgang Palm at PPG in the 1980s, was building its own DSP-driven instruments. The Waldorf Microwave 2, released in 1997, married wavetable synthesis to a Motorola DSP engine with results that were, in a different way, equally transformative. The sound was harder, more industrial, with an edge that musicians making electronic music in the European tradition found enormously useful. Roland released the JP8000 and the JP8080, bringing the virtual analog concept to a mass market at a lower price point. Korg released the Prophecy, the first monophonic virtual analog synthesizer, powered by its own custom DSP architecture. Within 3 years of the Nord Lead's launch, virtual analog had gone from academic curiosity to dominant paradigm. Every major synthesizer manufacturer was building DSP-powered instruments that claimed to model analog circuits. The TMS 320 family of chips, and their equivalents from Motorola and Analog Devices, had become the engine of the industry. The sound these instruments made colonized the 1990s. It is in the stabbing leads of mid-decade techno, in the slow filter sweeps of trance, in the buzzing bass lines of drum and bass and big beat. It is in records that sold millions of copies, and in records that circulated on white labels through record shops that no longer exist. It is in film scores and television themes and advertising music that played between the programs and lodged in the memories of people who had no idea what a DSP was. The specific timbral quality that DSP-based synthesis introduced, that combination of precision and warmth, of mathematical stability with organic movement, became so pervasive that it effectively redefined what people meant when they described something as sounding analog. By the end of the decade, many listeners were using the word analog to describe a quality that was, technically, entirely digital. They were describing the sound of algorithms. They were describing mathematics that had been performed on chips, built by a company in Dallas that had never written a note of music in its corporate life. There is a particular kind of creative discovery that happens only when a tool is used in ways its makers never intended. The history of music technology is full of them. The electric guitar was an attempt to solve a volume problem. The sampler was built for academic research and became the instrument of hip-hop. The Roland TB-303, designed to function as a practice tool for bass guitarists, achieved its now iconic acid house sound because the people who used it most were not bass guitarists at all, but producers who had no idea they were using it wrong. Texas Instruments and the TMS-320 belong squarely in this tradition. The chip was over-engineered for its original purpose. Military and telecommunications specifications demanded performance headroom, the ability to process signals faster than any current application required, against the possibility that future applications might be more demanding. That excess capacity, that engineering redundancy built in against hypothetical future need, was precisely what made it available for synthesis. The most interesting wrinkle in the story of DSP synthesis is what the limitations of those chips contributed to the sound. The TMS-320 series used fixed-point arithmetic, a method of representing numbers that is faster and simpler than floating point, but introduces small, systematic rounding errors into every calculation. When you are processing a radar return or compressing a telephone call, those rounding errors are insignificant. They fall below the threshold of any meaningful distortion. But when you are synthesizing audio, when the output of your calculation is going directly to a loudspeaker, those tiny errors have consequences. They introduce a specific kind of noise floor, a particular character of quantization, a subtle graininess to the waveform that, paradoxically, many musicians found enormously appealing. It was not the clean, sterile sound of pure digital audio. It was something rougher, more alive. Some of the most iconic synthesizer sounds of the 1990s, sounds that musicians still specifically seek out when recreating records from that period, were not the result of good engineering. They were the result of mathematical rounding errors being loud enough to hear. This is one of the stranger ironies embedded in the history of the synthesizer industry. The manufacturers of virtual analog instruments spent enormous effort and engineering time in their advertising and promotional materials emphasizing the accuracy of their digital models, how faithfully the mathematics reproduced the behavior of real analog circuitry. And yet a significant part of what made those instruments sound good was the degree to which the mathematics failed. The small inaccuracies of fixed-point computation. The aliasing artifacts introduced by sampling rates that were not quite high enough to be perfect. The way that certain filter designs behaved at the edge of their specified operating range in ways that were technically incorrect and sonically wonderful. Artists working with these instruments learned, by ear and by experiment, exactly how to find and exploit those imperfections. They developed patch settings that pushed the filter into instability. They found modulation rates that produced beating artifacts. They did, in the most literal sense, use the instruments wrong. And they made music that nobody who heard it could forget. Texas Instruments, throughout all of this, remained magnificently unaware of its role in the proceedings. The TMS 320 family continued to sell to its intended markets: telecommunications, defense, industrial automation, and the music applications, when they appeared in the sales literature at all, were listed as a minor and slightly puzzling footnote. There is no record of any TI marketing material from the 1990s that mentioned the Nord lead or virtual analog synthesis, or the revolution that had been quietly powered by TI Silicon. The company's focus was on its next generation of DSP architectures, on reducing power consumption for mobile applications, on the engineering problems of the present. The past applications of its chips, including the application that had produced some of the most beloved electronic music of the 20th century, were not the sort of thing that featured in a company whose culture was built around moving forward. TI was the engine, the musicians were the story, and the engine never knew. The TMS 320 family did not stand still. Through the 1990s and into the 2000s, Texas Instruments released successive generations of the architecture. The C2000 series for real-time control applications, the C5000 for low-power portable devices, the C6000 for high-performance computing. Each generation brought greater processing power, lower cost, reduced power consumption. And as the chips improved, so did the instruments built around them. What had required a full rack unit to process 4 voices in 1995 could by 2000 be done in a keyboard module half the size at twice the polyphony for a third of the price. The democratization of DSP synthesis followed exactly the curve that Moore's law predicted. Every 2 years, the same processing power in half the silicon at half the cost. The sounds that had been the exclusive property of well-funded studios in 1995 were in bedroom studios by 2000 and in the pockets of teenagers on their phones by 2010. The trajectory leads eventually to the software synthesizer, the plug-in running on a general-purpose computer processor that can model an analog circuit with more precision and more voices than any dedicated DSP instrument could manage. By the early 2000s, the CPU in a consumer laptop was fast enough to run the same mathematics that had required specialist silicon in 1995. The dedicated DSP chip became, for many applications, unnecessary. General-purpose processing had caught up, and yet something interesting happened as it did. The software synthesizers that musicians preferred were not the ones that modeled analog circuits most accurately. They were the ones that modeled the imperfections most faithfully, that reproduced the quantization noise, the aliasing, the filter instability that had characterized those early DSP instruments. Developers spent years not improving on the TMS 320's limitations, but reverse engineering them, reintroducing them deliberately, making tools that sounded like they were running on hardware that was 30 years old. The accidents had become the aesthetic. In 2026, the landscape of synthesis is almost incomprehensibly rich. There are software instruments that model analog circuits component by component, simulating the thermal noise of individual resistors. There are hardware synthesizers with DSP engines running billions of operations per second. There are AI-driven synthesis tools that can generate new sounds from text descriptions and modular systems with hundreds of interchangeable components and instruments that deliberately emulate the failure modes of hardware that no longer exists. The sound of TI Silicon, the specific quality of the TMS 320's arithmetic, its particular flavor of imprecision, is available as a paid download from dozens of plugin developers, each offering their faithful emulation of the thing that was itself an emulation of something analog. The layers of reproduction have become so deep that the original reference, The actual behavior of a real filter circuit in 1970 is almost beside the point. What musicians want is not the physics. What they want is the mathematics that approximated the physics 30 years ago and left its fingerprints on the sound. The broader lesson embedded in this story is one that the history of technology offers repeatedly and that the technology industry reliably ignores. The most transformative tools are rarely built for the purpose that transforms them. They are built for a specific, measurable, commercially justified need. In this case, radar processing and telephone compression. And they find their lasting significance in an application that nobody anticipated and that the people who built them often never knew about. Texas Instruments built a chip for the military-industrial complex and inadvertently built the instrument that would define the sound of a generation. The engineers who designed the TMS 32010 were optimizing for speed and precision in signal processing. They were not optimizing for warmth. They were not thinking about dance floors or studio headphone mixes or the specific quality of longing that a well-designed filter sweep can produce in a human being at midnight. They were thinking about nanoseconds and multiply and accumulate cycles. And yet here we are. The TMS 32010 was retired from production long ago. The companies that built the first instruments around it have largely moved on to newer architectures, more powerful, more efficient, generating less heat, consuming less power. Some of those original instruments still survive in studios and collections, maintained by people who find the sound of their imperfections more interesting than the sound of their successors' perfections. The Nord-Lead 1, in particular, has acquired the particular status that accrues to machines that were present at the creation of something important, not rare enough to be inaccessible, but old enough that every working unit carries a history, a story of the hands that played it and the songs that came out of it. They show up at auction and in the back rooms of music shops and in the corners of studios, whose owners are not entirely sure why they still have them, except that they do not want to find out what the music sounds like without them. There is a version of this story in which Texas Instruments is the hero, in which a company of engineers, working with military precision and industrial rigor, accidentally gave the world one of its most durable and beloved sonic tools. That version is true, but it is also slightly misleading, because it implies an intentionality that was not there. Texas Instruments did not give the music world anything. The music world took it. The musicians and instrument designers who looked at a telecommunications DSP and saw an oscillator and a filter, they are the agents of this story. They are the ones who asked the question that TI never asked, and built the instruments that TI never imagined, and made the music that TI never heard. The silicon was the possibility. The artistry was in finding the possibility and doing something with it that nobody else had thought to do. That sound in your music collection, the warm, humming sound that you cannot quite name, is the product of a chain of accidents so long and so improbable that it is almost impossible to reconstruct completely. It begins with the physics of speech and a team of TI engineers trying to build a talking toy. It continues through a military specification for a chip that needed to process signals faster than any existing application required. It passes through the hands of two Swedish engineers who asked whether the mathematics of a Minimoog could be computed in real time. It travels through the fixed-point rounding errors of chips that were doing their best and falling fractionally short. And it arrives, finally, in whatever speakers you are listening through right now, as warmth, as the specific quality that musicians and producers and listeners over 30 years have agreed to describe as the sound of something alive. It is not alive. It is arithmetic. But it is the most human arithmetic that silicon has ever been asked to perform. And for that, in the most indirect and accidental way imaginable, you have a semiconductor company in Dallas, Texas to thank.